Imagine waking up tomorrow to a shocking announcement from astronomers around the world. Deep in space, an invisible object has been detected moving toward our solar system. It isn't a comet. It isn't an asteroid. It's something far more terrifying, a black hole. At first, the news might not seem alarming. After all, black holes are invisible. They don't shine like stars or blaze across the sky like meteors. In fact, a black hole can only be detected by the way its gravity affects nearby objects. Yet despite its darkness, it possesses one of the most powerful forces in the universe. Months before it arrived, scientists would begin noticing strange disturbances. The orbits of distant planets and asteroids would start changing in ways that couldn't be explained. Space telescopes would track the source of these gravitational anomalies and eventually confirm humanity's worst fears. A black hole is approaching. As the black hole moves closer, its gravity begins affecting the solar system. The planets that have followed stable paths around the sun for billions of years would slowly start drifting off course. Comets and asteroids would be pulled into new trajectories. The delicate balance that keeps our cosmic neighborhood stable would begin to unravel. On Earth, the effects would soon become impossible to ignore. The moon's orbit could shift, causing tides unlike anything ever recorded. Coastal cities would face massive flooding. Earthquakes and volcanic activity could increase as the planet experiences unusual gravitational stresses. Scientists and governments would race to understand what comes next, but there would be little anyone could do. As the black hole enters the inner solar system, it becomes the dominant gravitational force. The night sky would transform into a scene from a science fiction movie. Stars behind the black hole would appear distorted and warped. This phenomenon, known as gravitational lensing, occurs because the black hole bends space itself, causing light to curve around it. The closer the black hole gets, the more dangerous its tidal forces become. Gravity does not pull equally on every part of an object. The side closest to the black hole feels a stronger pull than the side farther away. This difference creates enormous stretching forces. If Earth came too close, the planet would begin to deform. Oceans would rise in gigantic waves. The crust could crack under immense stress. Mountains, cities, and entire continents would be affected by forces beyond human imagination. Then comes the most terrifying stage. Earth begins falling toward the black hole. Contrary to popular belief, the planet would not instantly vanish. Instead, it would be stretched by tidal forces in a process scientists call spaghettification. Everything on Earth, oceans, buildings, forests, and eventually even the planet itself, would be pulled into long, thin streams of matter. Meanwhile, something even stranger would happen. Time itself would begin to change. According to Albert Einstein's theory of general relativity, strong gravity slows the passage of time. Near a black hole, this effect becomes extreme. To someone watching from safe distance, Earth would appear to move slower and slower as it approached the black hole. Clocks on Earth would tick more slowly compared to clocks elsewhere in the universe. Eventually, Earth would reach the black hole's event horizon, the boundary beyond which nothing can escape. Not spacecraft, not radio signals, not even light. For an outside observer, Earth would seem frozen at the edge of the event horizon, fading away as its light becomes increasingly redshift. But for anyone falling with the planet, the journey would continue inward. Beyond the event horizon lies one of the greatest mysteries in science. At the center of the black hole is the singularity, a region where gravity becomes infinitely strong and our current laws of physics break down. No one knows exactly what happens there. Some theories suggest matter is